All right, recording started. Today's topic, we will talk about low voltage overhead transmit or distribution system. So, so here by the end of today's lecture, we will be done with the overhead systems, or overhead as a transmission or sub-transmission and distribution. So as I would say, we call it transmission and distribution lines. Okay, so the distribution or low voltage will be basically anything related to value below than 1 kilovolts, which is, I would say, most likely commonly in Jordan as 400 volts, or sometimes we call it zero point 0.4 kilovolts. This value is line to line. To calculate line to neutral, this is will be 400 divided by root of 3, then it will be 230 volts. In old systems, in the past, it was 380 V line to line. So V line to neutral, 380 divided by square root of 3, which will be 220 volts. That was in the past. But nowadays, it's no longer 220. Nowadays, it's 230. That's what we are using so far. Now, in low voltage, this is the only one that there is a neutral line on it. When we discussed before extra high voltage, and medium voltage, there was no neutral conductor. But here in low voltage, there is a neutral conductor. Why there is a neutral conductor here? Because in the low voltage, we have something we call it single phase loading. For example, your home, your neighbor B to neutral, other neighbor C to neutral. Maybe some others they have three phase. If there is a large value of, so it depends on if you have. Okay, so again, if you have a large value of, if your home is consuming a large value of power, a large amount of power, then you will use three phase. But the standard is the single phase at home. Then here is, as we know, this is how it looks like, the low voltage. Then we can see in some systems there is 5 wires, some of them there is only, there's 6 wires. So it depends on different standards that I will talk about them today. The main components of the low voltage distribution networks are basically the poles, foundations, wires, connectors, insulators, stays, clamps, and wire arrangements. So the poles, again, the main usage for the poles is to carry the conductors and their accessories. Then the types, we have two types like steel and concrete. This is very similar to low voltage, to medium voltage. The medium voltage, we said there is a steel and concrete, then almost similar. Now the steel poles, there are two types. The first one, which is called light steel poles, and there is the other one, heavy steel poles. So light steels, as a shortcut, we will denote this by L2, which is L2 from lights. Then there are two types for this. So there's the first type with 10 meters length and the other one with 11 meters length. So we can see in this part, it can handle up to 408 kilogram force or kilogram Newton. This is, the lights, how it looks like, the light type. Then the other one, heavy. The heavy one, there is the same 10 and 11 meters, but you can notice a significant increase in the kilogram force. It was 401, now it is 550, which is almost 149 above the lights. 149 kilogram force above the lights. So again, light is we can donate it by L2, while heavy we can donate this by L3. So these shortcuts are important to recognize, to be recognized. So again, the heavy poles L3, right, light poles L2. So there's different type of diameters depending on the how much I mean the length. So this is how you cannot note that. How is this is a light pole? Look at the thickness is low compared with the thickness of this one. This is heavy. When you look at it, you will notice that this one is heavier. Now the other type, concrete poles. The concrete poles are used at starting, ending, corners, section poles, and it like intermediate poles. And these poles are no longer in service right now. I mean, no longer being produced because of their we had disconnected it because they are no longer because of their cost. So I would say those are old poles and no longer produced, but we still have them in service. Why? Because for the old poles that was in the past, then they were based on the concrete. But again, as I said, the concrete poles of low voltage are no longer produced. But we cannot say no longer used. Why? Because they are still usable in which is called in old lines when there is, I mean, a concrete conductor in the past that was in the past. The good thing about the concrete poles, they can handle a heavy force like 550, 550. But the drawbacks is the weight. When you look at the weights, 570 kilogram and 660 kilogram. However, when we talk about this, it was 200, 180, and here it was 162, 150. So we will say that the concrete poles are heavier than L2 and L3, the light and the heavy poles. They are heavier and they are more expensive. Okay, here's how the concrete poles looks like. Then again, the weights are heavy, but they can have the ability to, or I mean, to it can handle or can like a high mechanical kilogram force. So as we can see here, steel poles, concrete poles, the differences between them. Then you can look at the radius of L2. Here is L3. Here's concrete. Look at the radius of the concrete, how it is very big. Then it will be reduced when you go to the top. Then between L2 and L3, they are reduced, but you can notice that L2 has lower radius compared with L3, and that's normal because it is in L2 it can handle or lower mechanical force while L3 can handle higher mechanical force. Earthing of poles, as we already aware that in the medium voltage there was, I mean, earthing for the poles, then here is the same. But keep in mind in the network, there is a ground conductor. So we have a ground conductor um, in low voltage networks. Let's recall like something. So let's recall extra high voltage, medium voltage, and low voltage. High voltage, extra and extra high voltage, both of them, there was a ground conductor, or there is a ground conductor. Medium voltage, there is no ground conductor. In low voltage, there is a ground conductor. So the only power stage, there is no ground conductor, is the medium voltage. But keep in mind, even though there is no ground conductor, but the poles are grounded. That was in the medium voltage, which is basically the poles themselves. They are grounded to the ground, but no, there is no ground conductor. Here, earthing is grounded to the conductor. So how it looks like when you look at usually the ground conductor will be at the top, so then it will go inside the pole, then it will go down here to the ground, then to the grounding rod. Therefore all of the poles, they should be grounded, no matter if they are medium voltage or low voltage, they will be grounded. But the difference between medium voltage and low voltage, which is low voltage, a there is a ground conductor, while in medium voltage there is no ground conductor. Now, specifications of the pole foundations. So just here, like for your information, you're not required to memorize any of those in these two slides. So the dimensions of the foundation, 60 times 60 times 150. And when you need to dig using a machine, then you need to make sure 60 by 150. So we put cement. So here is the foundation, the ground level. This is the ground level. Then we will make it into different part, like foundation, like you see, like stairs. Then fill it with concrete, and so on. Now, how about the conductors? So how many conductors do we have? So in the conductors, let's talk about the conductors themselves before, then after that we'll talk about the wire arrangements. So we usually using three types or three sizes of wires. The first size, of course, all of them depending on the cross-section area. There is 100 millimeter square, 50 millimeter square, 25 millimeter square. Each one has its own ampere capacity. There's 271, 181, and 124. And each one has its own brand name. There is WASP, AUNT, and GNATE. Then we need to make sure to be aware of all of those. GNATE, or sometimes we call it GANET, AUNT, and WASP. You need to be familiar with the brand names, and all of them, they have 7 aluminum strands. So all of them, all aluminum alloy conductor. Then here is the conductor. Then there should be 7 strands. 1, 2, 3, 4, 5, 6, and the 7 in the middle. This is 7 strands. All of them, no matter if they are Garnet or GNATE or ANT or WASP, they will be like this. And here is it also. 7 strands, all aluminum alloy conductor. So again, we have GNATE, ANT, and WASP. You need just to be familiar with this. Each one, 25, 50, 100, and the ampere capacity, again, there is 124, 181, and 271. Now, let's talk about the joints. Joints, sometimes we can do them when the wire drum is done. Then we need to add another drum in the middle of the span, or we can use it when we do some repair. So let's talk a little bit about some joints. The first one, which is called mid-span joints. This joints, when we connect two wires together, we need to make sure when we do the mid-span joints, this must be placed at least 15 meters away from the point where the wire is attached to the pole. So if there is a pole here and a pole here, then we need to make a mid-span joints. Let's assume it's here. Then keep going with the other pole. We need to make sure that the distance from here to here, also like X, and from here to here, Y, X and y must both of them larger than 15. X larger than 15 and y larger than 15 is a must to make a midspan joints. Jumper joints, which is basically this is used to connect the ends networks of the junction cable. So jumper joints like can be like this. Here is the pole, then here's the end of the line, the end of the line. Here is the conductor. Then we make a jumper between them. This is a jumper joint. We call it jumper joints. There's another one, T joints. T joint we used to connect it to make to mount a ground station together, or if we need to make a new to make another power lines distribution point. So assuming there is a pole here, and there is, I mean, whatever you want to call it, like this one, then we need to make another part, which is either whatever you want to call it, transformer or any other parts. We will take another part. Here is another new line. Here is a conductor. This one, for example, comes from, I would say, like this point. Then this point, let's see how this one of the phases. It will take as a T-shape connector, or we call it joints, T-shaped joints. That's what's called T-joints or branching joints. So this is similar to paralleling. Like, for example, here is a source. Then you connect this to a load and connect another one to the load. Then look at this part. It looks like T. That's how T joints comes from. So you make it like this, joint, joint. This is a T joints. Again, we are using this in branching, or sometimes we call it paralleling. You need to connect a parallel line to the service. Okay? This is again the T joints. Then the other thing, repair sleeve. Repair sleeve, when there is a break in the strands of the wire, then we need to make sure um, to connect repair sleeve. So the thing, assume there is, here is a pole, and here is another pole. I'm gonna take just one phase of it. Then here's the line between them. Then if there is, for example, some cut in the strands, we can make a repair sleeve here. Then some cuts, we can make a repair sleeve here. Another cuts make a repair sleeve here. I mean, we can put multiple repair sleeve in the same span, but we need to make sure the breakage does not exceed 1/3 of the total number of the strands on the bundle. Just the thing that you need to make sure. Now, termination of the cable joints. So at the end, cable end, when the connecting to the bus bar, transformer terminals, or distribution panels for connections, we need to use the terminal cable joint. So again, here is like the startup of the lines, and here is, for example, the DT, distribution transformer, that goes to the distribution panel. Then from distribution panel, it will go as a feeder toward here. Then there should be a joint, which is we call it termination cable joints. We just put at the terminals of cable joints, at the end or at the beginning of the conductor. Now look how they looks like, the mid-span joints. You can see how they put jumper joints, the T branching joint, you see like a T, and the repair sleeve. So repair sleeve, there are several types like this. Keep in mind, when we install them, we will push here and push here, using the clamping them. Push here and push here, clamping. Push here and push here and here, here and here. So they will be clamped. So they will be fixed to be put as permanent. Now, insulators. Now, insulators, again, we are using them for two things. The first thing is to carry the conductors. The second one, which is a mechanical function, the electrical function to isolate it from the around us. So, insulators are basically isolate live parts from the poles and from the metallic parts. Then we need to use, or here we are using one type of insulators for a low voltage networks, which is porcelain. So I mean, as we know, there's porcelain, rubber, and glass. But as a standard, we will use only porcelain here. That is in Jordan. So it's called dual way. This is called dual way bobbin insulator. That's the name of it, which is again made from porcelain. Then the wire is fixed to the insulator at the starting, ending, corner, and section poles using a special tie called beginning or end tie when there is at the beginning or the startup, while the remaining we call a straight line tie. Here is how the insulator looks like. Again, it's called dual way bobbin insulator. This is how the again the low voltage insulators looks like. So here's like the pole body will be installed here. Then this is how it can take the conductor, go through it. Then here we need to make sure we can to make a bending when you go to the conductor, which is tie it very well. We call it bending sometimes, or something like tight it. So we need to make sure it should be binded in this way. So the first thing when we bind it, we used to make it like bind the first stage as 5 centimeters, then do another tie 2.5, then 5 centimeters. Then here we will make this goes out. Though, so when we do this tying, then this is the standard tie for low voltage networks. Okay. Here, this is tie in terms of we have beginning or ending of the line. Only end or beginning of the line. But if you are in the middle, it does not require that much tie. I mean, I would say like we can use it, tie it like this way, putting beginning like this way, and just like do the bending in a regular way. Stays, the purpose of the stays or tension rods is used to maintain the alignment of the poles to make sure we need to prevent this from sag or deviation because of the position or the tension on it. So those are the stays. Stay wire. Then mechanically can handle it. Now, let's look at the other thing, which is when we look at the phase sequence or I would say, the conductors, you will see 6 lines. Some of them there are six, some of them there's five. So what are those six or what are those five? So number one, this is the earth or the ground. Number two, phase A, then 3B and C. Sometimes they call it RST or ABC, whatever you want to call it, that's fine. Then the number five, this is street lights. The street lights, and the last one, this is the neutral. So there are six. Sometimes some of them there is five without the street light line, but I would say like Earth must exist for all of the lines, so of course it's mandatory. A, B, C, and neutral, all of them are mandatory. Sometimes there are street lights cabled, sometimes there is no. So it depends whenever needed, whenever it depends on the design as well. Then we can look at the distance in millimeters between the earth wire and the top, which is 140 millimeters, or in other words, 14 centimeters. Then between the other phases, 32 centimeters, etc. The other cables. So again, there are 4 or 6 cables, 6 conductors, I mean. Okay, so let me show you another picture for them, the little back. This line is still under installation, so there is no thing here. 1, 2, 3, 4, 5. This one, there is no street lights. That's why this one is earth, this one A, B, C, and a neutral. There is no ground. This one, 1, 2, 1, 2, 3, 4, 5. Of course, the same thing. There is no street lights. So then, not all of them there is street lights. So this is, I would say, earth, RST, or A, B, C, then a neutral. Okay, then again, they can be 5 or 6 wires, depending on the like if there is street light or not. Again, the tires, they can be G-nets. What else? Let me remember. G-net, ant or wasp. Now we already talked about the stays. Now let's talk about the type of the stays. Um, there is at the beginning, end and corner, they are permanents, and we can notice this a lot now around us. I mean, the low voltage poles around us, if it is in the corner, end and beginning, there should be stays or permanents. Now there are some other stays that can be temporary. So the temporary, like when there is an inability to install a permanent stay due to the presence of valley or street sections, then we're using temporary. There is sometimes the pole itself, inability to install or a permanent or temporary faults. There is an angle, so one stay is used if the network deflection angle is less than 60 degrees. If more than 60 degrees, we will use 2 stays. That's something that we need to think about. Then there is a temporary when we have a maintenance. So again, if you are at the end or at the startup or at the sections, then we will use stays depending on the angle, more than 60 degrees or lower than 60 degrees. If it is more than 60 degrees, we'll use 1 stay. Lower than 60 degrees, or I'm sorry, more than 60 degrees, we'll use 2 stays. Less than 60 degrees, we'll use 1 stay. Now again, the wire arrangement, as I said, there is a ground line, 3-phase lines, street lights, and a neutral line. So most likely the wire line has a lower ground line, a very low thickness, or I would say like diameter. The diameter of the 3-phase lines, there is 100. If it is WASP, or there is, I mean, a G-net 25, or it can be ANTS if it is 50, depends on whatever needed. So we can see the next one, street lights, and the last one is the neutral. So the street lights line, which has a low diameter, a lower, I'm not saying, I would say like a lower cross-section area. Now we will talk about subnetworks. What we discuss here about the main network. What do I mean by a main network? What do I mean by subnetwork? So basically, you can say, assume this is a distribution transformer that's converting 33 kilovolts to be 0.4 kilovolts. Then, in this part, you will see multiple feeders. Feeder 1, feeder 2, for example, feeder 3. Then in the same feeder, you will see a subnetwork, like lateral 3.1, lateral 3.2, which is the same thing that we discussed before, but this one is in distribution. Here, the feeder, which is called main network, Those two are called subnetworks. Then here in the subnetworks, you will see most likely as a T joints here in these lines. Then it will go to homes, home 1, home 2, etc. And depending on the phases, home 1 for phase A, home 2 for phase B, and so on. So this is kind of different than what we discussed on the high voltage to medium voltage, which there was a feeder, lateral, the distribution transformer, and the customer. Now, now the situation is different. Sometimes, to avoid the confusion, I can, replace the word F or the number or the letter F by saying, mentioning this is main M1, M2, M3, which means main circuits. And instead of mentioning L to be in safe level, I can call this as S31, S32. Then we can go to the customer. Here is customer 311. Here is customer 312, and so on. And of course, depending on the phase, are we in single phase loading or three phase loading? All of them matters. In subnetworks, since it's a subnetwork, there is no need to use, the big size on all of the conductors because they are just a sub feeders, sub lines. Therefore, subnetworks. Then we will use lower ratings around 50 millimeter square on the three phase lines. Then in this situation, we are saving more money. More money because when you are reducing the cross-section area, you are saving more money. Then the thing about it here in the subnetworks, somebody can say, okay, why we are reducing the ratings? Why we didn't keep it like this? If you make it as 100 millimeter square, you can apply KCL here. Assume this one can handle 278 amps. Then you cannot say this one 278 because when you, according to KCL, when you put the currents, you will say that here is IM, here is I1, I2. You can say IM equals I1 plus I2, which is 278 plus 278. This will be more than 500. 540, 556 amps. So you can say there is no way, because this one, the sum of 556, and here this is 278, which does not make sense for us. Therefore, we are reducing the size to be low. When you reduce the size to be low, then it will be around 160 something, 160 something, or I would say 120 something, 120 something. Then when you add them together, there will be less than 278. That's the point when you do the KCL. Therefore, will you reduce it? Then here is how's the connection. Again, we have the earth, phase A, B, C, or RST. Then there is a neutral, and this is for the street lights. And when the street lights, you will see RST. What does it mean? Which means it can be any of those, not all of them, of course, no. There will be any of those. It can be either R or S or T. That's the thing that you need to think about, which is for street lights. And of course, this should be attached to a meter. Then we can, watt meter, they can detect how much the lights streets are consuming. Then they can take the money for the money policy or for the government, so they can pay for the street lights fees. Okay, this is again how the interconnection, the distance between the clamps, as I said, between earth to top 14 centimeters,
Then between conductors 32. Just keep this in mind. Now let's talk about the electricity meters. The electrical meters, and here we will talk about the old meters, which means does not include, we don't talk about smart meters, no smart meters. So I'm talking about the old meters that was used in the past, and it's still being usable for some areas right now. The power company are trying to replace it by smart meters, trying to replace all of the old meters by smart meters. Um, the old meter was including the equipment, these components, which is the current coil, voltage coil, permanent magnets. The current coil, which is basically turns with a large cross-section areas, and it is connected in series with the electrical circuits. Basically, it will tell you how much the currents. The voltage coil, which is basically it's connected in parallel, and it is basically to measure the voltage. And permanent magnets, this has a deflection movement or a rotational movement that makes the meter working. And this, which is in that disk, and that disk is connected to the grounding or to the counter. This is the aluminum disk, and there's a number set that's connected to it. Here is how they connect the three-phase and with 4 wires and three-phase 3 wires. The thing about the fourth wire, which is basically the neutral, then this is how we see the connection. The working principle of the electricity energy meter, when the energy meter is connected to the grid, the current flows through the current coil. This causes this rotation, creating a magnetic field. That magnetic field is directly proportional to the currents. Then the current flows through the voltage coil, generating a magnetic field to the circuits that causes the movement. So these two magnetic fields interact with the aluminum disk, inducing eddy currents into the disk. These eddy currents are directly proportional to the strength of the magnetic field. Therefore, the magnitude of the currents flowing through the coils. As a result, disk rotates on its axis at a speed directly proportional to the strength of the secondary current or directly proportional to the consumption. The shaft is connected to the gears, which are linked to the number sets, records amount of energy consumed into the circuits. So again, this is only associated with the low voltage level, and it's only associated with the old meters. But nowadays, in the smart meters, we're no longer using this. We'll use different technology. Okay, now I believe we are done with the low voltage level. Any question? Okay, that's great. So tomorrow, I would say in Sunday, inshallah, we will continue explanation. Most likely on Sunday, I will go through the protection overview, which is file number 6. That will be next lecture, inshallah. Let me stop recording. Talk to you a little bit about the exam.